Example number 2. 2a, we are going to use the steps to solve it. Okay? 2a has a shortcut that I'm going to show you afterwards and talk about when this shortcut can be used. If you don't want to ever use the shortcut, it's fine. You can use the steps all the way through. 2a is a little bit different than our first example because there's 3 logarithms as opposed to 2 logarithms. So step 1, right? We've got all of our steps listed here. Step 1 is, can you write things as a single logarithm? Yeah, no problem. So on the right side, I have log x plus 6 plus log x minus 1. And I could look at my log laws and say, hey, when I'm adding 2 logs, that's the same as multiplying. So I can write x plus 6 times x minus 1 inside of the logarithm. So I've combined the right-hand side to a single logarithm, but I still don't have a single logarithm altogether. If I want to get a single logarithm altogether, the only way I can combine logarithms is if they're on the same side of the equation. So I'm going to subtract the log 6x over to the other side. If I do that, does it make sense? I'd be left with 0 on the left-hand side. And then do I have a log law for subtracting? Yes. If you subtract 2 logs, that's the same as dividing. This was step 1. Writing things as a single logarithm. We write it as a single logarithm to prepare ourselves for step 2. And step 2 is changing to exponential form. What's the first number I'm going to write when I change to exponential form? 10. Which is the weirdest thing because you look at the last equation, there's not a 10 written anywhere. So that's part of the reason why step 2 is so hard. The base is 10, the exponent is 0, and the answer is x plus 6, x minus 1 over 6x. There is step 2. That's the hard step. And it's hard because we look at from step 1 to step 2, now our equation looks completely different than what it did before. That's one of the reasons that step is so hard. And now we can start step 3. We can start solving this. What is 10 to the 0? It's 1. And the equation that we have is a rational equation, something you solved in grade 11. What do we do to solve rational equations? Well, you'd probably want to get rid of that fraction. You can multiply both sides by 6x. That would simplify this on this side, and we would get 6x equals x plus 6, x minus 1. So we notice the rational equation. We used a strategy to get rid of the fraction. Now we've got another kind of equation. What kind of equation is this one? This one is going to be a quadratic equation. And so how do we solve a quadratic equation? Well, we expand. And then in order to solve a quadratic equation, you have to make one side equal to 0. So even though it was factored before, it wasn't equal to 0. We have to first make it equal to 0. And then we'd have to refactor it in order to solve. Minus 3 plus 2. X is equal to 3, and x is equal to negative 2. So all of this is supposedly the easy part of solving log equations because it's all review. It's all stuff you've done before, solving equations with equations you've seen. Rational equations or quadratic equations.
I was just wondering how you got rid of the log and got 10 to 0.
So from step 1 to step 2, that's just using the definition of a logarithm. When I write a logarithm as a single logarithm, log base 10 of this equals 0. The 10 is like the base. The 0 is the exponent because logs solve for exponents. And what's inside the logarithm is the answer. So I'm just using the definition of a logarithm to change from log form to exponential form. And that's when we introduced logarithms for the first time. The first thing we did was, this is the definition of a logarithm. The final thing we need to do, step 4, check for extraneous roots. So we have to take our answers and plug them back into the original equation. So if I plug in 3, I have to plug in that 3 into 3 separate logarithms to check if I ever get a negative answer. Here I'd have 18. That's fine. 3 plus 6, 9. Fine. 3 minus 1, positive 2. Fine. Since I have a positive number in each of the logarithms, I can say that this one is okay. Now I have to check negative 2. Negative 2 times 6, negative 12, that's bad. I don't even have to check the other ones. As soon as you get a negative inside of a logarithm once, that answer is going to be extraneous. So now we've solved this completely. Now I want to point out something, because some of you are developing a bad habit right now even though you don't know it. Okay? We have done 2 examples, and in the 2 examples we got 2 extraneous roots. In the second example, our extraneous root was negative 2. In our first example, our extraneous root was negative 3. And you've been listening to me, and you've heard me say taking the log of a negative number is bad. Okay? Sometimes your brain cuts things short, and you might just in your head go negative number bad. Right? You're just like, oh, I'll listen to every other word. And Mr. JR said negative number bad. What happened in the first example? Negative number bad. Second example, negative number bad. And so you get into a habit that if you get a negative number, you're just like bad and cross it out. Okay? That's not the case. I can make up an example out of my head where you get a positive number and a negative number, and the positive number is bad. Okay? I can make up an example with 2 positive numbers, and they're both bad. I can make up an example with 1 number, positive, bad, or 1 number, negative, bad, or 1 number, negative, good. So just because the answer in the end was negative and we've canceled it out because it's bad, you always have to plug it in. It's only bad if you take the log of a negative number. For example, consider this. Is it good or bad? It's good. Oh, positive, good. All right, I'll give you a bigger positive number. Good or bad? Bad. Right? Because if you plug in 5, you'd take the log of a negative number. What about if I put in a negative number? Good. Because 3 minus a negative 7 would be 10. That would be good. In fact, this is the answer to this equation, if you wanted to solve it. The answer is negative 7. And that's the only answer. And it's good. So I want to be careful with that, because I've noticed that with these examples, and I think even the next example has another negative answer that gets canceled out. It might make you think that just because an answer is negative, it's bad. That's not the case. You always have to check your original equation, plug it back in, and see if it works. Okay. So we did step 1, step 2, step 3, step 4 in this one. Whoa, that's not what I wanted to do. Go back. No, that's not what I wanted to do either. Whoa. Okay, one more try. There we go. Make it a little smaller. Now you can't see it at all. That's okay. Zoom back to regular size. Still pretty small, but you can see it there. Now there's a shortcut in this one. And the shortcut can happen right here. I'll do it in green. I'm going to go, so because this is equal to this, I can say, sounds like someone else is doing math. So 6x is equal to x plus 6 times x minus 1. What did I do? Well, can you see that on this side I have log of something, and on this side I have log of something? If log of something equals log of something, does it make sense that the two somethings have to be the same? In this situation where you have that, and only in this situation, you could do this right away. How many steps does that save us? That much. All of step 1, all of step 2, and part of step 3 gets saved in that step. So it is a big shortcut. But then after that, everything else would be the same. Does that make sense? Now that shortcut only works if you have like a log of something equals log of something else. If I added plus 1 to that equation, poof, shortcut no longer works. You have to use the long cut. I don't know if that's a word. You have to use all the steps. Okay? But if it does happen to be this situation, then you could just buy, same thing that we used when we had the same bases, right? If I have the same bases, a power on this side of base 5, power on this side, the exponents have to be the same. We used that strategy earlier in the unit when we were solving exponential equations. So it does happen in log equations too. But if you like to always use the steps and get really good at the steps, you can use that as well. It will always work. So let's look at part B. Do it on a new page. Wait for it. Come on. All right, here we go for part B. Step 1. Combine things as a single logarithm. Sometimes you already have a single logarithm. First of all, this is a log equation because the x is in a logarithm. Do we have a single logarithm? No. We have 2 logs on the right-hand side of our equation. Can I combine them? Yes. What's my log law for adding? Log law for adding is multiply, so I would have log base 2 of x plus 2 times x. Extra brackets if you like. I have a single logarithm. Step 1 completed. Go to step 2, the one that you're going to forget. Use your definition of a logarithm, change to exponential form. What's the base? 2. What's the exponent? 3. What's it equal to? And I'm going to multiply that out. X squared plus 2x. Start step 3. Solve for x just like you normally solve for x. What's 2 cubed? Well, that's 8. What kind of equation is this? Oh, it's a quadratic. I solve quadratic equations by making one side equal to 0. Can I factor? Or quadratic formula. Luckily, this one factors. Plus 4 minus 2. X equals minus 4. X equals 2. So all of this, step 3, solving for x. The last thing we need to do, step 4, we need to check, are any of these extraneous? Plug in negative 4. Negative 4 plus 2 is negative 2. Once again, just by coincidence, the negative 1 is bad. But you always have to check it by plugging it into the original equation. X equals 2. 2 plus 2 is 4. That's okay. Plug in 2 into the other one. It's okay. That one is good. Questions for practice on this one? 11 and 13.